So thank you, Michael, for the introduction. And actually, my presentation will continue where Ilya is ending, namely with measurement relevance for electricity grids. And you may also wonder, Ilya stating about ppm accuracy parts in 10 to the 6, is it really relevant at all? Is there really a relevant industrial need for that? And I hope after this presentation, you'll be convinced that there's at least one application, namely the loss measurement of power transformers, where this is really highly relevant. I acknowledge my colleagues, in particular Ernst Houtzager, who made crucial contributions to the realization of what I'll be presenting today. So I'm working at VSL. We are the Dutch National Metrology Institute, and one of our focuses is energy. And we are very active in energy gases, chemistry, flow, but also very active in electrical energy. And this presentation is part of the focus of our institute. So the outline of my presentation, first of all, I'll give a little bit of background on why are power transformer losses important. And then if they're so important, then of course you need to determine them, you need to measure them. So how do we measure them? And what is the actual measurement challenge? Once we have this background, we need, you'll understand why these measurements are very important. And that's why, of course, then also why these measurement systems need to be calibrated. And I'll share some on-site experiences of this kind of calibrations and end with conclusions. So this is, I would say, a sketch of our electricity supply system. It starts with power generation, conventional generations, but nowadays also wind and solar generation. And then there's a power transformer to scale up the voltage to the level of our high voltage transmission system. And the high voltage really helps to reduce current and thus to reduce losses. And that's why we have the high voltage. But then, of course, at the place of use in our distribution system, we need to scale it again down to the level that we can use it. So power transformers are really key components in the grid. When it comes to power measurement, first of all, there's metering. There's energy measurement from the electricity supplier to the transmission system operator. There's an energy measurement point when it goes to the distribution system. And of course, in our industry and our homes, we have electricity meters to measure the power. So that's the first part where power measurement comes in. Billing or revenue metering is a very important part of our electricity grids. But then the other element, and that's the focus of my presentation today, is power transformers and the losses in these power transformers. So why are power transformer losses so important? Well, actually, when I started in this field, I was, say, quite surprised to find out how much the cost of these losses are. And I came to this presentation of, at that time, ABB, which showed that the purchase cost of a power transformer can be even less than the total cost of the losses. So the total cost of ownership for a utility of a power transformer is not only the few million euro for a large power transformer, but there's an equivalent amount of money or even more related to the losses. And of course, these losses have to be supplied. So that also relates to CO2 emissions and an environmental impact. So that was also recognized in the EU, where they did an impact study and found that the losses of the power transformers in the grid in the EU amounts up to half of the energy consumption of a complete country, Denmark. So this is just one component, power transformers, and a very significant amount of total losses. So that's why they said, okay, we want to limit these losses. And in order to achieve that, they say we'll put requirements on the minimum efficiency that a power transformer should have. So by now, already since more than 9 years, there are hard requirements on the efficiency of a power transformer in order to be allowed to install it in the grid. And actually, this is a certain table, they call it the peak efficiency index, with a particular calculation. I won't go into the details, but you see here in the graph, as a function of the rated power in MVA of the power transformer, there is a certain minimum peak efficiency index. And that is not only, say, an EU requirement, but similar requirements are now also part of the IEC 60076 series-20, where they also mentioned requirements on efficiency. And so given these large impact of losses on the cost of ownership, the utilities that buy the transformers put requirements on the losses. So if an actual power transformer has a loss which is above the guaranteed loss by the manufacturer, as part of the contract, they will give a fine to the power transformer manufacturer. And to give an indication of this cost, suppose that we have a reasonably large power transformer of about 100 MVA with a guaranteed loss of 500 kilowatts, or 0.5% loss. Then the typical fine is €10,000, $10,000, this order of magnitude per kilowatt that is above the required or the agreed guaranteed maximum losses. So assume if you now have a 3% uncertainty in your measurement, then 3% of my losses, 500 kilowatt, times this fine adds up to €150,000. So already the measurement uncertainty of 3% is corresponding to a very significant amount of money. And mind you, this is 3% of 0.5%. So this already amounts to 150 ppm, 0.015% of the total power. So 150 ppm is 150 kilo euro. So this is where you immediately see 1 part in 10 to the 6, which is extremely accurate, is already corresponding to €1,000, say, uncertainty or possible fine for the power transformer manufacturer. So if you want to do a reliable loss measurement, you really need very high accuracy in order to achieve the confidence that you would like to get, and in order to minimize the debate between the customer, the utility, and the power transformer manufacturer that is producing the power transformers. So given this importance, the loss measurement of a power transformer is a very important part of a factory acceptance test of the product, of the power transformer. And this is the way this loss is measured. So you have the test transformer here, you have a power supply, you apply a voltage, and you measure the current that is running. Well, a rather straightforward approach. And then, the voltage is in the kilovolt range, the currents are very high. So very similar to what Ilya already showed, we need a voltage divider, we need a current transformer in order to be able to get to a 100 volt, 1 amp or 5 amp level that can be handled by sampling wattmeters. The sampling wattmeter, or the wattmeter that Ilya showed, in itself already has voltage and current scaling. So this is additional current and voltage scaling in order to be able to allow the measurement of very high voltages and high currents that are applied. And to give you a certain impression about typical equipment or some equipment that is being used, here the voltage divider on the left-hand side, where the high voltage capacitors are a key part, the sampling, digitizing power meters. There are many power meters on the market nowadays, and current transformers to scale the high current to the level that can be handled by this power meter. A typical measurement range up to 100 kilovolts, up to 2000 or even 4000 amps, so very significant currents. So this is the system that is used by actually the power transformer manufacturer to verify his product. And of course, he's not allowed to, as a butcher, to check his own meat. So when he is doing this calibration, often the utility that is purchasing the power transformer is witnessing the measurement in order to assure or to verify that the measurement is really done correctly and that the numbers on the test report are really reliable. Well, when it comes to reliability, there is, of course, a requirement on how accurate should this measurement be. And the key requirement comes from this IEEE standard that really requires 3% accuracy in the loss measurement down to a power factor of 0.01. And there are similar statements in the IEC standard. An overall maximum error of 3% may be achieved. Eco-design directive relevant for Europe states something about 5% accuracy. So there are, in summary, accuracy requirements on this loss measurement set by written standards, which are industry agreements, and legislation, the EU requirements, that is part of legislation. But typically, to give, say, a ballpark number, this IEEE number is of 3% and a power factor of 0.01 is taken as the reference, as kind of the minimum required accuracy. And then what does it relate to the measurement challenge? Again, I'm referring to the formula already shown for sinusoidal waves by Ilya. Power is current times voltage times cosine phi. And we're now not energy metering, not billing, but we are now measuring losses. And here I indicated the schematic. I mean, for an ideal inductor or power transformer, the current would be fully perpendicular to the voltage, 90 degrees. But in reality, there are some losses, and that causes the phase angle to slightly deviate from 90 degrees. So phi is roughly 90 degrees, and you can phrase it also as 90 degrees minus alpha. And if I then do this, and this cosine 90 degrees minus alpha can be approximated with roughly alpha, the phase angle. And this is the key, say, the key formula for power transformer loss measurements. Because voltage and current, these are large numbers, and to measure these with 1% accuracy is not really that difficult. However, this phase angle is very small. For example, for a power factor of 0.01, the phase angle is roughly 0.6 degrees, and then 1% uncertainty suddenly becomes a challenge, because that relates to 6 millidegrees, 100 microradian, or industrial often used minutes, 0.3 minutes. And mind you, in metering requirements of current and voltage transformers, it's like 10 minutes. As Ilya already indicated, in energy metering, phase doesn't come in, it's all about magnitude, but here it's all about phase, and the phase requirement is really stringent. So that is, I would say, one of the key messages of my presentation. In loss measurements, it's all about phase accuracy, and you only can achieve high accuracy in the loss measurement, good reliability, if you have a low phase error. So effectively, these transformer loss measurement equipment is designed to have a very low phase error. So that's what I, again, indicate. The system here, the aim is less than 3% at this power factor, which corresponds to a phase accuracy of around 300 microradian, 1 minute. This is the IEEE requirement. But then, of course, the industry of the manufacturers of this kind of test equipment make sure that their equipment is meeting this requirement. So that will be at least 3 times more accurate. And if you then, so then you end up with the roughly, say, the 1% and the 0.3 minutes that I indicated before. So the power transformer manufacturers have this equipment, but then that still not automatically means that the equipment is indeed meeting the requirements that are set by the IEEE or by the utilities. So they want an independent verification of the accuracy of this industrial measurement system. And that's where we metrologists come in, where calibration come in. And this traceability to international standards is mandatory in the IEEE and IEC standards. And the rationale behind this requirement is what I showed in the very beginning. If you want to do a reliable test, and this test has an enormous impact financially and also environmentally, you should really be sure that your equipment is traceable to national standards. So we should calibrate it. And to calibrate a loss measurement system, there are two two approaches. The first approach is component calibration. So here you have the voltage divider, the current transformer, the wattmeter, so you can individually calibrate them and then add up the uncertainties to get an idea of the accuracy of uncertainty of your total loss measurement system. Relatively easy to perform. The uncertainty evaluation is pretty complex, and also not all effects are covered. So that's why we moved to the system calibration. Calibrate the system as a whole. It's more difficult to perform, but that's what I would say. That's the challenge for the metrologist. But the advantage for the industry is that they get a certificate with just the overall uncertainty of their system, which is much lower than if you would just add the uncertainties of the individual component calibration. And then, last but not least, there is the important aspect that all effects are included. We will be calibrating the system on site in the actual use, in the actual environment, with the actual cabling, so that the calibration is really representative of the actual use. And as you might already have guessed, these components, I mean, a wattmeter you can ship, but these voltage and current channels and all this cabling are not really easily shipped. And also, the testing in a power transformer manufacturer site is going on continuously. So it is, well, apart from weight, there are also time aspects. If you remove the equipment from the test lab, the power transformers cannot be delivered, testing is stopped, the delivery of products is stopped, which is a huge financial impact. So on-site calibration is the way to go. And how are we doing such a system calibration? What is the approach? In order to make that clear, I again draw the picture of the typical loss measurement of a power transformer. And then what we are doing in the calibration is the following. We are replacing the power transformer by our loss measurement system or reference system. What we do is we measure the applied voltage and then generate a current. Again, phantom power, like Ilya explained, we generate a phantom current to the current transformer with a phase that can be adjusted. So we can apply exactly 90 degrees, no losses. We can adjust the phase so that we can have any losses and that we can calibrate the loss measurement system under any losses that are relevant for the particular power transformer manufacturer. This approach was pioneered by NRC Canada. They made an analog system with analog current comparators, and at VSL, at some point, we decided to also go in this route, but then instead of the analog equipment, went for digital sampling, which really, in the end, worked very well. So both the NRC Canada and VSL Netherlands system use this approach of simulating a power transformer with certain losses to the measurement system of the industry. So at power factor 1, I already mentioned 3% is to be achieved. So the specification by the instrumentation manufacturers, so the manufacturers of voltage divider, current transformer, this part here, the TLMS, they typically are 0.5 to 1%. So if you want to make a sensible calibration, you need to be at least, again, 3 times better. So that's where the reference should be the level of 0.3% really in order to make a sensible calibration. So again, the advantage, it's more complex to perform than individual component calibration, but it does lead to a smaller overall system uncertainty. So how does it work in practice? So this is the schematic. At the top end, you see the system of the power transformer manufacturer. So there are 3 channels. It's a 3-phase measurement. And what you do is you put all voltage channels in parallel and you apply a voltage. And then you put all current channels in series and you apply a current with adjustable phase through all 3 CTs in series. And then the challenge in the calibration is to simulate this power transformer with adjustable losses. So to generate a current with an adjustable phase angle with a very stable low noise phase angle, and also with an accurate value so that you exactly know what the losses are you are applying. So to this end, we measure the voltage, we do digital signal processing in order to get a driving signal for the current circuit here. And then, of course, there's a feedback system. We measure the actual applied current and compare it to what we would like to have. And if it's not exactly the phase angle we would like to have, we adjust our driving signal in order to get it right. One of the things that I learned from Eddie So, the late Eddie So from NRC Canada, is that this calibration is so important that should you find that this system of the customer really has a large deviation, it is not an unlogical question that the customer says, well, what about your system? Are you sure that my system is deviating? Are you sure that not your system is deviating? So to that end, we add another verification measurement with a second current transformer and a reference wattmeter so that we can compare the readout of our current generation and measurement system with, again, an additional wattmeter CT. So we have two readings, and that is found extremely relevant in practice and also extremely useful. It's an indicator for us doing the calibration to what extent our reference system is really consistent and giving highly accurate results. So the range of the system, 100 to 230 kV, 2000 amps. I already mentioned the key part of our system is the digital signal processing. That's the heart of the setup. That's where all the intelligence is. Really difficult to completely develop. But then by calibrating all the components and by getting low noise through the digital signal processing, we were able to presently achieve 20 microwatt per VA, 0.2% at power factor 0.01. And the advantage of the sampling and the automated of the sampling approach that it can be fully automated. So once we've set a current and a voltage, we can automatically adjust phase angle and do the calibrations. Really helpful in speeding up the calibrations. So how does the system look like? These are a picture of the components. So first of all, the voltage channel, a high voltage capacitor with low voltage electronics. The intelligence is in FPGA software in the NI digitizers. We have the power amplifier and the current transformer to generate the high currents. We measure the actual applied currents using current transformer, again, 3-stage active compensation in a similar way as Ilya was explaining. So every stage may be accurate to 1%, but then 3 stages means an accuracy of 1 ppm. These transformers were also made by NRC, crucial components in our setup. And then the verification measurement using a reference wattmeter at the bottom of the rack. And then at the very top here, you see this is all the equipment packed and ready for shipment to an on-site site. Looking at the uncertainty budget, you clearly recognize the 3 components: voltage scaling, current scaling, power measurement, and then there's, of course, the total system. You have noise in the system. You will not be able to have, say, negligible noise in your current phase angle generation. We are now able to do it with a few ppm, a few microradian really, but there's still a noise contribution of a few ppm. But if you add them all up, they're at the level of 0.15% at power factor 0.01. And you see the main components are comparable. I mean, we have voltage scaling, power measurements are less accurate than the current scaling. And I always, in my uncertainty budget, account for some unknown effects. I call it the nightmare of any metrologist, that there is something you're not aware of and you're underestimating your uncertainty. So, but with this budget of 0.15%, we end up right now with a CMC claim in the BIPM KCDB, the database containing the calibration claims of the National Metrology Institutes. Our claim is 0.2%, which is well below of what is required. The remind you, the industrial systems are 0.5 to 1%. So this is also the uncertainty required to really do a sensible calibration. But mind you, this 0.05% means 5 ppm. So if there is any doubt that in the power measurement, for example, or in voltage and current scaling, say ppm level measurements are not relevant for industry, in this particular application, every ppm does come in. I'll conclude with showing you some on-site experiences, my colleagues making up the current circuit, implementing here, putting our equipment high up. You see here a power transformer, and you can also get an indication of the scale of such a high voltage laboratory. It's extremely high. Equipment is here, so it's a special environment to do the calibration. And you also see, hey, that cables are really non-negligibly long. We typically have 10, 15, 20-meter cables. And moreover, it's in an industrial environment. So our voltage measurement is using triaxial cables in order to really shield all unwanted influences, and also not to be sensitive to ground loops and grounding, because in such an industrial laboratory, you will not have a common, well-defined ground. The ground in one corner of the lab is really different at the ppm level that we are measuring than at another location. So grounding is extremely important. So it's one sentence here, but it's actually maybe even more than a year of work to find out all the details that are relevant to get ppm accuracy in an on-site measurement. So far from trivial. I already mentioned the automation. With our present system, we can really cover a lot of voltage, current, and power factor combination, more than 400 points in roughly 2 days. This is the EU industry that we have been servicing with our measurement capabilities. And say one particular example I would like to show that I'm particularly proud of, and I see that one of the colleagues where I've been doing the calibration is online. So this is the calibration on site of a 700 kilovolt reactor measurement system. And here you can see my former colleague, Gouillet. He is a 2-meter tall guy. This rack is about 1.7 meters. So again, you see an indication of the huge instrumentation. Just the measurement instrumentation. These are 700 kilovolt high voltage capacitors, or minute 200 kilovolt reference, and our generator up to 150 kV. And the actual current circuit is located here, and here is our current generation circuit. So this is the system where we say one of the most demanding calibrations, where the customer really would like us to get the 0.2% accuracy. In order for them, it's very important because of this argument that I said, if the calibration, if their loss measurement system is extremely accurate, proven by a traceable calibration, there is less discussion with the customer, and they can readily, say, independently prove the quality of their products. So this is how a calibration looks like: an applied voltage for a certain current, and then errors as a function of power factor. So for a reactor system, it is low current, but for a power transformer system, the current goes up to 2,000 amps. And you can see here, so there's a certain voltage, a certain current, and then as a function of power factor, the errors of the different ranges, and then the 3-phase total error of the system. What we typically do is that these test points are agreed together with the customer, because we want to be sure that we take those test points that they mainly use in the verification of their products. With that, I come to an end. So power transformers are key components in our grid with significant losses, and the industry is using loss measurement system to verify these losses. And of course, you need a calibration in order to make sure that this loss measurement is really reliable. And well, measurement-wise, the key challenge of this particular calibration is phase. And the 3% is a requirement from IEEE. Via system calibration, we are able to get to the 0.2% uncertainty at this power factor, which is really needed by the most high-end power transformer manufacturing industry. With that, I would like to thank you for your attention. And I also would like to end with acknowledging the extensive finance support we got for EU projects, Trafolos, and the presently running Ensure. And all this work is also part of our network on smart electricity grids. Thank you.